Okay, so any matrix P with non-negative entries such that each row sum is equal to 1 will be called a one-step transition matrix, or simply a transition probability matrix. So our goal is to define a stochastic process XM, a discrete parameter stochastic process, indexed by non-negative integers, with initial distribution as A and satisfying Markov property, time homogeneous Markov property that is, with one-step transition probability matrix P. So in other words, we want for each k in S, AK to be the probability of X not equal to K, and for each N in the set of all positive integers, we want this conditional probability equal to this conditional probability. And both of them should equal to Pij. So this is essentially the Markov property, and the fact that it doesn't depend on N makes it time homogeneous. And of course, this MP should hold provided the conditional probabilities are well defined, which is, it's enough to say that the first conditional probability is well defined. Now the problem is that this description is too complicated. Every time we give this description, we have to say that left hand side is equal to right hand side provided they are well defined and both of them are equal to Pij. This makes the whole thing extremely complicated. We have already seen, just to show that the row sums of the Pij is equal to 1, that's a very simple fact. We have to actually first make sure that, we take an n such that probability of xn plus 1 equal to j conditioned on probability of xn equal to I. This conditional probability is well defined. We have to take such an n and then we have to give the proof. So for more complicated proof, this will become a nightmare if we give this as a definition. So this is, although this is what we want, this is not going to be a good definition. This whole entire description is extremely complicated. So therefore, the remedy is to take a slightly different path and arrive at the same definition. So we are going to do that. So before doing that, we'll do a quick calculation. Suppose XM is indeed a stochastic process with initial distribution A and it satisfies the Markov property, time homogeneous Markov property with one-step transition probability matrix P. If that's the case, then it's first thing that will happen is that for any, so what we'll do is that we'll try to compute the, so let me first tell you what is the goal. So the conditional probabilities, although they, the Markov properties in terms of conditional probabilities, they are slightly complicated to handle because every time you have to say whenever the conditional probability is well defined, you have to left hand side is equal to right hand side and so on. So therefore, it's better to talk about the joint probabilities instead of conditional probabilities. That's what we are going to do. Okay. So before doing that, let's do this calculation. So let's fix an n in the set of all positive integers. So let's fix a positive integer n and let's take I0, I1 up to In in S such that this joint probability is positive. Okay. Actually, I should take all the way up to In minus 1. Sorry, that's a typo. It should be In minus 1. Anyway, so take this guy so that this is positive. So then, actually, we need all the way up to In for the next calculation. It's fine. It's not a typo. All we need is this probability should be well defined so that the conditional probability that all the conditional probabilities that we use will make sense. Okay. So now instead of the conditional probability, let's look at the joint probability all the way up to In. So x0 equal to I0, x1 equal to I1, all the way equal to In. So let's use chain rule. If we use chain rule, we'll get this. This is the probability of x0 equal to I0 times probability of x1 equal to I1 given probability of x0 equal to I0 times probability of x2 equal to I2 given x0 equal to I0 and x1 equal to I1 and so on. All the way up to the last conditional probability. Okay, this is just the chain rule. Now note that since this event has positive probability, all of these conditional probabilities are well defined, because all of the other conditioning events are actually bigger events compared to this guy. So if this guy has positive probability, all the other events will also have positive probability, and therefore all the conditional probabilities that are used here are well defined. Now use the Markov property. Using MP, we get that this is okay. This one would be just depending on x1. So here, this is the present. This is the future. This is the present, and this is the past. So past will go away. So this will just become x2 equal to I2 given x1 equal to I1. Similarly, all of them will change like that, and the last one would become xn equal to in given xn minus 1 equal to in minus 1. All the other ones will just go away because of Markov property. Now, we know that all of these conditional probabilities are well defined because of this assumption here. So therefore, they will all become different Pij's. So the first one is the initial distribution, that's AI naught. And then this is just the transition probability from I naught to I1. So this is Pi1 I naught, I naught I1. This is just the transition probability from I1 to I2 and so on. The last one is the transition from In minus 1 to In. So this joint probability will be given by this expression. So if indeed we have a stochastic process with initial distribution A satisfying this MP, then the one-step transition probability matrix looks, and one-step probability transition matrix P, then the joint probabilities look like this. Now suppose we have a stochastic process taking values in S such that the joint probabilities have this form. Let's call this equation MC. Now note that for joint probabilities, we are not putting any restriction. We are just doing for all I1, I2 up to In in S and for all N in N. If that happens, then firstly, it's very easy to check that the initial distribution of x0 is actually A. Why? The probability of x not equal to k is just the sum of probability of x not equal to k and x1 equal to L when you take the sum over L. This is just law of total probability, the first equation here. Now this is just one-step transition probability. So sorry, this is just the joint probability. So let's use the joint probability with n equal to 1. This is true for all n. Let's use it for n equal to 1. So this will give you AK times PKL. Now of course, in this sum, this is a sum over L, so AK will come out and this will become a sum over L. Now sum over L of PKL is 1. We know that. That's it. P is a transition matrix. So therefore, this is AK. So in particular, what this tells you is that if MC holds, then XM has initial distribution A. Now we claim that if MC holds, then also MP holds. Of course, MP holds provided the conditional probabilities are well defined and so on. So we'll prove it, but the idea of, let me give you the idea now. The idea is that since if MC holds, so we got this MC from MP, right? If MP holds, then we've calculated these joint probabilities. And now we will see that if MC holds, then MP holds. So in other words, instead of giving this complicated description using conditional probabilities, we can as well give this description using these joint probabilities. And that would amount to giving the Markov property. Subject to this claim, of course. We'll prove this claim first, and then we'll use this as a definition of a Markov chain. So that's our plan.